Welcome to The Explainer. Today, we are diving into the really cool world of organic chemistry. We're going to look at two chemical families that are super closely related but act completely different from one another: alcohols and ethers. It's a story that really shows you how the tiniest little changes can have the biggest impacts.
All right, let's kick things off with a puzzle that really gets to the heart of what we're talking about today. Imagine you have a box of Legos. With the exact same set of bricks, you can build, say, a car or a house. In chemistry, this happens constantly. So the big question is, how can the exact same atomic ingredients create two things with completely different personalities?
So to crack this puzzle, we've got to meet the two families in question. You can think of them as chemical cousins. They come from the same family tree, they have the same number of atoms, but they have these very different defining features that control pretty much everything they do out in the world.
And here it is, that family formula. See, both alcohols and ethers can be described by this one single general formula. What this means is that if you have a certain number of carbon atoms, you're going to have the exact same number of hydrogen and oxygen atoms, whether it's an alcohol or an ether. They're literally built from the same kit.
Okay, now this is where it gets really interesting. Look closely at the tiny but absolutely critical difference in how those atoms are put together. For alcohols, you have an oxygen and a hydrogen atom just kind of tacked onto the end of a carbon chain. That's called a hydroxyl group. But for ethers, that oxygen atom is actually sandwiched right in between two carbon chains.
That little arrangement of atoms has a name. It's called a functional group. And believe me, this functional group, it is everything. It's the molecule's command center, it's the source of its personality. It's the part that dictates what it does, who it talks to, and how it's going to react. That simple little OH versus that O makes all the difference in the world.
So we know what they are, but how do we talk about them? To make sure there's no confusion, chemists came up with this universal naming system called IUPAC nomenclature. It's basically a guarantee that a chemist in Tokyo and a chemist in Toronto are talking about the exact same molecule when they use its name.
And the naming system for alcohols is just beautiful. It's so logical. It's not about just memorizing a bunch of random rules. It's about telling a story with the name. It's all about finding that main carbon backbone, the one that's holding that all-important hydroxyl group, and then giving that group top priority, like the lowest possible address on the street. Any other branches? They're just side notes. It's like giving every single molecule its own unique, unmistakable address.
All right, let's circle back to our puzzle and talk about one of the most powerful ideas in all of chemistry. It's called isomerism. And that's really just the official, fancy name for our Lego brick problem. Same parts, totally different structures.
So let's get specific. Take this formula: 4 carbons, 10 hydrogens, and 1 oxygen. Seems simple enough, right? But how many totally different, stable molecules can you actually build from that exact list of parts? Well, the answer might surprise you. And this is where the magic really happens, because you've got different flavors of isomerism. You can have chain isomers, where the carbon backbone itself is branched in different ways. You can have positional isomers, where that functional group just moves to a different spot on the same chain. Or, and this is the big one for our story today, you can have functional isomers, where the atoms totally rearrange themselves to form a completely different family of molecule.
And here it is, the grand reveal, the solution to our opening puzzle. That exact same formula, C4H10O, can be arranged to make butan-1-ol, which is an alcohol, or it can be arranged to make diethyl ether. They are functional isomers of each other. Same parts, totally different machines.
Okay, so we get it. They're built differently. But why does that matter? Let's dig into why that one tiny structural change creates such a massive difference in how they behave, especially when you try to mix them with water.
The whole secret lies in this special kind of connection, called a hydrogen bond. The best way to think of it is like a really powerful chemical handshake between two molecules. Now, it's not a full-on bond that makes a new molecule, but it's a super strong attraction that holds molecules really close together.
So here's the crucial part. That hydroxyl group, the -OH on an alcohol, has a hydrogen atom stuck right onto a very electronegative oxygen atom. And that's the magic ticket. It allows the alcohol to form those powerful hydrogen bond handshakes with water molecules. This is why small alcohols mix perfectly with water. They're what we might call social molecules. They just fit right in.
But ethers? Oh, they're a totally different story. They're more introverted. Their oxygen atom is buried between two carbons. Critically, it has no hydrogen attached directly to it, so it can't offer that handshake to form a strong hydrogen bond with water. And the result? Ethers don't mix well at all. They're insoluble, and that right there solves the puzzle we started with.
Now, this unique OH structure doesn't just decide if it can mix with water. Oh no. It gives alcohols a whole set of chemical superpowers. That exposed reactive group lets alcohols transform into completely new kinds of molecules through some really specific reactions. So this table here, it's not just a boring list of reactions. Think of it more like a chemical choose-your-own-adventure for an alcohol. By just tweaking the conditions, a little more heat here, a different partner there, we can steer that molecule down completely different paths. It's not just one thing, it's a starting point for a whole family of transformations. And this is what I find absolutely wild. Look at how sensitive the outcome is to the conditions. You crank the heat to 180 degrees Celsius, and a water molecule gets ripped right out of a single alcohol molecule. But if you drop the temperature just 40 degrees to 140, now two alcohol molecules get together, they lose one water molecule between them, and they form an ether. It's such a subtle change with a completely different result. And the last superpower on our list is oxidation. But here's the catch. It's not a one-size-fits-all kind of reaction. The product you end up with depends entirely on the alcohol's classification. Basically, it matters where that hydroxyl group is attached. Is it on a carbon connected to one other carbon, two others, or three?
And this just shows you again, structure is destiny. Primary alcohols, where that OH group is hanging out at the end of a chain, can be oxidized once to something called an aldehyde, and then all the way to a carboxylic acid. Secondary alcohols, with the OH group in the middle, they stop at a ketone. And tertiary alcohols? Well, that carbon with the OH group is just too crowded with other stuff, so they don't react at all.
So from how it dissolves in water to the way it transforms into other chemicals, that tiny, tiny little difference between an ROH and an ROR structure dictates a completely different life path, a completely different destiny for each and every molecule.
So what's the big takeaway here? The next time you see a chemical formula, just remember that's only the list of ingredients. The real magic, the story of the molecule, is all about how those ingredients are put together. That's what decides if you get a social molecule that loves water or an introverted one that just keeps to itself. It's an incredible reminder that in chemistry, just like in life, it really is all about the connections.